we move on to the next topic, which is power management. And power management is very important in wireless, and we will see it in every standard that we talk about, starting with this one. And basically, the scheme works as follows in all the standards. Is that a station, when they want to save their battery, they say, I'm going to sleep. They tell the base station generally that I'm going to go to sleep, and the base station then saves their frame. If a frame comes to them, the base station saves it, and every so often the base station announces, basically in the beacon, it announces that I have frame for station number 1, 5, and 3. And if station number 1, 5, and 3 wake up, or any one of those wake up, they just say to the base station, look, I am awake, please give me my frame. They get the frame and then they go back to sleep. Either that, or 135 can wake up and say, well, do you have any frame for me? And if there is a frame, the base station gives them the frame and then they go back to sleep. So either way, the sleep coordination requires coordination between the base station, or the access point in this case, and the sleeping station. Access point, if knows that the station is not off. See, there are two kinds of stations. One, the station which have gone away forever, and the second, the stations which are sleeping. Sleeping stations are really here, but they're sleeping, right? So they are treated differently than people who have not come into this room at all, or walked out of the room, right? So let's see power management. The station tells the base station its mode. It says I'm in the power saving mode. I'm going to go in the power saving mode, and the mode changed by the power management bit in the frame control header. So every frame that is sent has a frame control header. We saw that in the beginning, just before the duration field. In the frame control header, there is one bit which says, look, I'm going to go to sleep. And after that, any packet that are received are buffered, and the access point broadcasts the list of stations with buffered packets in its beacon frame. In its beacon frame, there is a bit map. So let's say there are 20 stations in this network. There is a bit map of 20 bits. Each bit indicates for whom I have a frame. And the access point has a frame waiting, one or more frames waiting. So when you wake up, you listen to the beacon, and if the beacon has your bit set, then you just ask the base access point for that frame. Alright? So that is the traffic indication map, TIM. The subscriber station, SS, subscriber station, this is the mobile station. Sometimes we call this mobile station, sometimes we call it subscriber station. Sends a PS pole message. PS is the power save pole message to the access point, which sends one frame, and so access point will send one frame. The more bit in the frame header indicates that there are more frames. So every frame also has a frame control header in which there are many bits. One of them was, we already saw, was the power saving bit, but there is one bit called more bit, which tells that this is one frame, but I have more frames for you. Alright? So please stay awake. I'm going to send you one more. With 802.11e, unscheduled automatic power save delivery, SS transmits the data or null frame with power saving bit set to 0, and the access point transmits all buffered frame for the SS. Now with 11e, it can send multiple frames, right? And therefore all of that can be done in one sweep. Whenever you wake up you ask for a frame, you get all of the frames. With scheduled APSD mode, access will transmit a pre-negotiated time schedule and no need for polling. So now there is there is another mode for sleeping here, and that is the mode where we negotiate that you will wake up every so many milliseconds. At that time, basically you wake up and we will give you all the frames. There is no need to poll, as opposed to in the unscheduled polling where we will just listen for the beacon and figure it out. All right. So here you just say, well, I'm going to be off, much longer now. So you think this allows much more savings because you don't have to wake up at every beacon to listen to your bit pattern. Hybrid APSD mode, where PS pole for some and schedule for other categories. So you also have hybrid mode. Now here is the thing. This is all 11, and I am not sure which part of this is implemented. And this hybrid thing reminds me again of something. So what happens is now there is a hybrid mode where you allow both, and I don't know whether all the products implement this mode or not. Because this is the kind of thing which goes on in IEEE. In IEEE they put everything. And then Wi-Fi group will remove much of this stuff. Simplifies lots of stuff, right? So for example, this whole PCF and HCF concept is in 11 but not in Wi-Fi. Similarly, this hybrid APSD mode, I'm not sure. So anyway, there are two kinds of modes. In one mode, you listen to the beacon, you find your bit on, then you say, give me my frames, and you get the frame, right? In the scheduled mode, you just say, I will come back up after so many milliseconds, and then you come back up at that millisecond and you get your frame. All right? There is no need for polling. So this is polling less, and that is one with polling. And obviously the first mode is already implemented. Basically the stations do go to sleep, and their times are announced in that map. So that I know is done, but I'm not sure about the other parts, whether it is implemented or not. Then we move on to the next new standard, 11N. 11N stands for next generation of 11, actually, which is just convenient. It happened to be N. 11N is 4 to 5 times faster than ARG, and the reason this is 4 to 5 times is because there was lots of question mark about some features which we'll talk about in a minute. So first thing is, it uses a code which is much better. So it uses 64 QAM with 5.6 code rate. What does that mean? So you remember QAM. We discussed QAM here in the file layer, and QAM was 16 QAM, and then we had 64 QAM, 256 QAM, and so on and so forth. As the time passes by, we are able to do higher level QAM because of the digital signal processing. So right now this is the limit. This standard is brand new, so it shows you right here that the limit is 64 QAM for low prices. Actually, you can always do 128 and 256, but that would be generally done for military, which has unlimited money. For most of us who want $5 device, 64 QAM is the limit. So 64 QAM with 5.6 code. So basically 64 QAM gives you 6 bits per hertz, but you only use 5 bits. 5 bits you use, and the 6th bit is used for error correction. And 2 spatial streams. So 2 spatial streams is this MIMO thing we talked about. 2 streams in parallel. 40 megahertz channel. That is another feature, which is that instead of having one channel, you use 2 channels. So use channel 1 and 6 together. So instead of 20 megahertz, you use 40 megahertz. And 400 nanosecond guard interval, that is the interval between the transmissions or frames, gives you 270 megabits. Now, having said all this, not everybody agrees that this is what needs to be done. So you might get an 11N which doesn't do 40 megahertz. Alright, there was a big discussion about 40 versus 20, because with 40 what you're going to do is, if everybody started using 40, there are only 3 channels. Remember, 3 non-overlapping channels, 1, 6 and 11. If everybody started using 2, then nobody else can do anything much, So obviously 2 people cannot do 2 at the same time, right? So this 40 megahertz is there in the standard, but there was a big discussion whether this can be done all the time. MIMO is kind of always done for all 11N devices. They have multiple antennas, and I have shown you some here. And the major components, so these are the 10 major things that the 11N does. First thing it does is better OFDM. Better OFDM, and which means the PALM 64 coding, and it gives 65 megabits instead of 54 megabits, higher code rate. So that was the business of 5 by 6, code rate of 5 by 6. Previously we probably did 2/3, now we are doing 5/6. So that gives you better than 54. Second thing it does is space division multiplexing. So space division multiplexing is how much parallelism can you have, up to 4 spatial streams. So you could have up to 4 antennas. Diversity, more receive antennas than the number of streams, and select the best subset of antennas. So it also allows you, while the streams could be 4, you could have 8 antennas, for example, and then take the 4 best out of those 8 antennas. Beam farming, we talked about beam farming. Anybody remembers what is beam farming? What does it allow you to do? Dynamically direct. Right? You can change the direction by the seconds, by the milliseconds. Focus beam directly on the target antenna. MIMO power save. Use multiple antennas only when needed. So you might have 4 antennas, but each antenna requires power, so you may just use 1 antenna. But if you need more traffic, if suppose you get a lot of traffic, then you can use 2 antennas, 3 antennas, 4 antennas. So you can put antennas on sleep. Right? Not the whole station. You could put the whole station on sleep too. So basically, so that is another flexibility we have with multiple antennas. Channel bonding. Channel binding is basically this using 2 channels at the same time. So we transmit on both channels. Aggregation, transmit bursts of multiple data packets. This was already there in EDCF. Short guard interval, and so we wait smaller interval before we start the next frame. 400 nanoseconds instead of 800 nanoseconds. Reduced interframe spacing, and greenfield mode where eliminate the support for ABG. So here's what happens is that most of the time if you buy an equipment, it has to support the older standards as well as the newer standards. And that reduces the speed, because if you have to support A, B, and G, then many of these spacing, etc. will not work. And it turns out that if you have a mixed clientele, so for example, you have some stations which do not understand N and some understand N, what will you get overall? Not understand N, basically. You get the lowest speed of all. And so if you have some stations which understand B and don't understand G, but you have a G, the rest of them understand G, what do you get? You get a B. So that's the thing, is that if you either you upgrade everybody to the latest highest speed, or you get the lower of the 2 speeds. If you have mixed stations, which is always the case, when you have mixed station, you get the lower speed. And so if you don't support for ABG, then you get all this 200 megabits stuff with all these special features. But if you have other stations, then you get lower speeds. What are the 2 spatial streams? No, all this is saying if with 2 spatial streams you get 270, but the standard allows up to 4 spatial streams, right? So spatial stream, if you remember MIMO, no, 4 rays, let me call it this way. If you remember MIMO discussion, in MIMO if you have multiple antennas, so if you have only 1 antenna, then only 1 spatial stream can go, from this antenna to that antenna. But if you have 2 antennas, then you can have 2 spatial streams, going 1 from this to that and 1 from that to that, right? If you have 2 by 2, you have 4 spatial streams. This is not the limit. This is saying that you can get 270 megabits with this set of parameters. And it allows up to 4 spatial streams. And remember, with 4 spatial streams, you just don't get twice as much of 2 spatial streams. Remember, we told you that if you have 2 by 2, that is 4 spatial streams, but you get only factor of 2. Because you get almost the minimum of the two numbers. If you have two antennas here and three antennas here, you have 6 spatial streams. But you will only get factor of 2 because you get the minimum of 2 and 3. Then there is 11P, which is wave, wireless access for vehicular environment. Basically, this is a standard which is I had the standard status in the previous slide. Let me just double check the status. P. This is not approved yet. So this will be approved in November 2010. So this is still in works. I mean, it's still in development. So this will allow you to exchange the data between the vehicles and the roadside infrastructure, and it can be used for toll collection, commercial transactions, safety services, and the main thing is that it allows you a speed of 200 kilometers per hour. I think that's too high a speed, but anyway, for up to that speed, up to 1 kilometer. That is the distance up to which they cover. Basically, every standard when you design, the previous 11 standard, for example, were I think more like 100 meters or 200 meters, but this is longer. Right. But here's the thing, though. I mean, I don't want to say access point because I will have to verify. This might allow ad hoc mode, where you can talk from one car to the next car. In that case, the distance between the two cars. So there is something called dedicated short range communication, DSRC standard. So this 11P is used in the lower two layers of that standard. It uses 5 to 10 megahertz channel at 5.9 gigahertz. So this frequency is higher than 2.4, and the channel size is smaller. And I don't understand why did they select smaller channel sizes. Actually, there are two things which are different here, and I already figured it out. One is that this frequency band is not the complete 5 gigahertz band. So the previously which we had shown you the frequency band that was ending at 5.85. So this is higher end of that 5 gigahertz spectrum. They have selected especially for this reason, and then they have selected a smaller channel. So the standard is not out yet, but this is just, right now it is making quite a, let me say, quite a bit of wave, in the sense that I see lots of papers being published, quite a bit of activity in this area. Then the next standard to know is the fast BSS transition. And this allows you to move from one access point to the next access point without breaking. So this is just the same way like it does on the cell phone. When you're driving, you really are passing from multiple base stations, but you never know because your call continues. Similarly, on 11, but on 11, right now, when you move from one access point to next access point, the call disconnects. But if they implement 11R, then you will be able to move quickly without losing the connection. Then there is a mesh mode, 11S, and the mesh mode means that one station, and the signal can go from one station to the next station. So for example, here there is a home network, and the traffic which is coming from somewhere else could be sent from this home to that home, from that home to that home before it reaches to this home. So that is called the mesh mode, and it's generally used by military and the emergency people because they may not have base stations, and they are not allowed to have base stations, particularly the military people. If they have base station, the first thing that will be bombed is the base station. And therefore they want to really run in an ad hoc mode in some sense. And so this is a mesh mode, is a special mode where basically you go from one station to the next station. You could also do in the enterprise where you could have multiple buildings which could be transmitting stations, transmit traffic from one to the other. And so 11S is has the facilities for this. It has special security because the traffic is going through other people's home, other people's devices. So for example, your traffic is coming through your neighbor's device, so you really want to be sure that they don't get your data. Therefore, it generally is encrypted, and so there is a lot of discussion about the security. Then the beacon and the probe has been modified so that you know what mesh you belong to, and how the protocol, how the packet will be routed. Packets will be routed, and there is 6 address scheme instead of 4. Previously, we talked about 4 addresses. Remember, the transmitter, the receiver, the source, and the destination. Now they have the mesh tunnel beginning, mesh tunnel end, and then the source and the receiver. So the mesh tunnel begins at some point and ends at some point, and then there is a source and the destination, and then there is a transmitter and the receiver. Includes route discovery, route maintenance, and route recovery. So how do you go from one house to the next? They have to exchange some packets to figure out who can hear whom, what is the signal strength, and what is the best path. All that detail is here. And then the hybrid mesh protocol for layer 2 routing combines tree-based routing and AODV routing. So we haven't discussed AODV routing. We will be discussing that when we talk about layer 3 in wireless. So basically, there is a whole set of protocols for routing in the wireless. And 2 of them are, one of them is this tree-based, and one is AODV, distance vector. So this is a distance vector routing, and we will discuss this when we are finished all with the data links and we move to the routing layer for wireless, which will be after we have discussed LAN, PAN, WAN, MAN, and so on and so forth. Then we'll move to the layer 3. So there we'll talk about the routing protocol, and so that is used in this mesh network as well at layer 2. So anyway, the wireless mesh network again is more theory than practice, and the reason is because 2 reasons. First of all, nobody trusts their neighbors to be forwarding their traffic. Second thing is, nobody is interested in forwarding the traffic for the neighbors because there is no money to be gained. So because there is no economical model for mesh, its use is limited to the 2 things that we talked about, that is the military and emergency response. Yeah, so what they do is, this is what is happening. Now one more thing which is happening is, everything that was in layer 3 is being moved into layer 2. Now, so for example, you heard of OSPF. OSPF is the layer 3 routing, right? Ethernet has adopted it. So if you buy a latest Ethernet equipment, I mean, you won't buy it probably. You say a carrier buys the latest Ethernet equipment, it does routing at layer 2, so that way you can have a country-wide Ethernet. You could have Ethernet where packet is sent from San Francisco to Boston and never leaves Ethernet layer. Right? So that is another way the layers are breaking down, is that every layer wants to be independent. So basically the Ethernet people don't, I mean basically they want to be independent of the IP layer, and they want to be covering the whole area, while the Ethernet was designed to be local area network, but now they have become wide area network. And so they have adopted the higher layer into themselves. Does that make sense? So basically, similarly here, when you have a wireless network, it could depend upon IP and to find the route from A to B, but 802.11 wants to have its own way of finding a route from A to B. Suppose a packet is coming from Japan and going over this wireless networks to China, let's say, just to be extreme, right? So when I want to go from on this wireless network and I still have to do multiple hops, I would use my layer 2 facility. So this will be a one link actually for the IP. A wireless router word means it is a layer 3 device. A wireless router or wired router knows IP. Okay? And it will be using the IP layer mechanisms. A wireless access point and a wireless station, they are not supposed to know IP. Right. They are doing this routing. Right. Alright, so I wouldn't call them wireless router. They are just the access point. Right. They are layer 2 devices and they are doing routing. Let's say there is a router at the beginning of the wireless network. Right? It speaks both layer 3 because it is talking to some wired thing on the other end, right? So it speaks IP. Now it has to send over this mesh wireless. So it is going to give its packet to layer 2. Alright? Now the layer 2 could be just one wireless hop and that's done, that's easy, right? But now it's a multi-hop. So the layer 2 will figure out those multiple hops. For layer 3, it is still the IP header will not be touched. Okay. That is, this whole thing is one link. So based upon the layer 2 header, this whole multi-hop will take place. Alright, so what is the definition of mesh? One more time. Definition of mesh is when the clients themselves transmit the signal to other clients. So there is always in the wireless network, there is generally a service provider, the carrier, AT&T or something like that. And if and then they give the signal a connect to the clients like us. In the fixed wireless, it could be a home. And so, but when the clients connect themselves to other clients, that is called the mesh network. Alright, because there is another concept called relays, where the carrier transmits from one tower to their own another tower. And from there it comes to the client. That is not a mesh, even though it is 2 hop. So not everything which is multi-hop is a mesh. Alright? So the key thing which distinguishes mesh is actually multi-hop for sure, is that the destination is not the next, it could be more than 1 hop away on the wireless, but that it is done by the clients, not by the service provider. And 11S, because this is client, because your signal is going through other clients, you really need to be secure. So one of the first thing 11S does is it adds security, and the 11 security standard is called 11I, and this one actually adds. Now here's the thing, we are not going to be discussing the security in this class, and the reason is that we have so many things to discuss just in the wireless aspect that we leave the security for the security class. So this one is, now for example, when we discuss 11I, at that time we have to discuss what is a key distribution center and what are the keys and how they are shared and all that. So since we're not going to discuss that, I'm just going to briefly explain that basically the way it works is that everybody has a password or a key that identifies them, and so they share that with the KDC, which is the key distribution center, and then the key distribution center authenticates you, saying that yep, you are the person, you are saying who you are, and so that is the kind of mechanism which is used. Beacons and probe responses to advertise the mesh ID, the routing protocol, the security capabilities, etc. So we know what is a beacon. Beacon is something that is sent by the base station, and probe is what is sent by the subscriber station. So you could send a probe and saying that is there a Wi-Fi available here, and the base station would advertise a beacon saying that Wi-Fi is available here. So one or the other way, and both are not necessary. So for example, most often it's the beacons which tell you what is available, and anybody can listen to those beacons and figure out what is available. But sometimes for security reasons they don't announce the beacons. Alright, so this is one of the options in your own wireless networks. When you set up 802.11, it has an option whether do you want to announce the SSID, and you could say no, I don't want to announce it. In that case, the receiver has to know the SSID and it will send a probe. So it will, suppose then the receiver knows that it has to look for Wi-Fi, then it will say, is Wi-Fi available here, and that's the probe. Alright, and then the base station will respond. So that is a little bit more secure, because when people say what are the networks available, they find blank. They don't see that network on the screen because nothing is being announced. Right? But it is there, and so you ask for it and you get it. So the distinction between probe and beacons is clear. Right? Beacons is announced by the base station, probe is sent by the subscriber station. Alright, so that is the beacons and the probe to advertise mesh ID and so on and so forth. Use 6 address schemes to accommodate mesh tunneling. We already had 4 addresses, now there are 2 more addresses to get from beginning to the end. Includes route discovery, route maintenance, route recovery, and mesh routing. Basically, now every station has to know how to get from A to B, so they need a path. Right? Generally, 11s just talk to the base station, and the base station possibly knows how to get to the next hop, but now everybody has to know the next hop. So everybody does what we call layer 3 operation, but it is all done in layer 2. The routing is done in layer 2. And so there are 2 protocols for layer 2 routings. And actually, not 2 protocols. The 2 protocols are combined to make 1 protocol. There is tree-based routing and AODV routing to combine to make something called a hybrid wireless mesh protocol routing, HWMP. Alright, and we will discuss these routing when we come to the layer 3 for wireless.